All right, let's get started here. First of all, I want to extend a warm welcome to each of you as we embark on this journey through the technical landscape of generative AI. Um, Thank you all for being part of this webinar. Our exploration will commence from the fundamentals, progress through the evolutionary strides of AI, and culminating in the current era of generative AI. And I hope you all will find it enlightening. I start most of my webinars on generative AI with this picture, which, by the way, I generated using Stable Diffusion. This was based on Elon Musk's statement or tweet a couple of years ago, around about the time when OpenAI was born, when he tweeted that we are like a group of people walking carefully on a frozen lake towards the shore where there are riches to be had. If each one of us think that, if I reach the shore earlier, then I can have all the riches myself. If each one of us think like that, you know what might happen? The surface would break and we all would fall into the lake. So what he was referring to was the frenetic pace with which AI systems, especially generative AI systems, are being developed today, with little or no regard to human safety, security, and privacy. Incidentally, yesterday was OpenAI's first ever, actually, day before yesterday, was OpenAI's first ever developer conference in San Francisco, where they reiterated the importance of safety, security, and privacy. However, I think there are still a lot of uncertainties. Well, today we are not focusing much on the safety and security aspect, maybe a little bit, but then mostly on the technology aspects of generative AI. So without further ado, let's get to it. This is the diagram that gives you a glimpse of all the AI tools out there. And the outer circle shows the modality, basically text, audio, image, video, code, and so on. And within each modes, the spokes actually divide them into different application categories. The research sector, the research is where it shows the foundation model space with OpenAI, Anthropic, Stability AI, and Hugging Face, and so on. And some of these tools like the Midjourney, DALL-E for image generation, GitHub Copilot, Replit for code generation, etc., are quite popular. Okay, so let's start with the basics. All right, so let's start with the basics here. So the left part of the slide shows the biological neurons found in the human brain. So they are the basic building blocks of the nervous system and are responsible for transmitting information through the electrical and chemical signals. And on the right side, you see the perceptron. Perceptron is a simplified mathematical model inspired by the functioning of the biological neuron. In biology, the strength of the connection between two neurons is determined by what is called the synaptic efficacy or the synaptic strength. Stronger synaptic connections means that the signal from the presynaptic neuron is more likely to influence the postsynaptic neurons firing. So the synaptic strength is analogous to the weights in artificial neural networks. So the neurons in the biological context have a certain threshold of excitation that must be reached in order for them to fire an action potential. So you find something analogous in the form of the activation function, f of x. So in this particular case, the weighted sum of all the inputs, if it exceeds zero, then the neuron is fired. So, or in the perceptron case, the signal is, the output is a 1, otherwise it is a 0. All right, so we know what a neuron is. So what is a neural network? It is a mathematical framework designed to recognize patterns and make decisions based on the input data. A neural network consists of interconnected nodes, which are organized into layers. As you know, each node in the layer is the neuron that we just saw, or the perceptron. The connections between the neurons are associated with weights, which, as I mentioned before, determine the strength of the connection between the neurons, and they play a crucial role in learning. So when you say that the network is learning, you're actually seeing an effect in the weights being adjusted. So during the learning process or the training process, the network adjusts these weights based on the error between the predicted output and the expected output, and the actual target, sorry, the expected output and the actual target. So this is typically done using optimization algorithms like gradient descent. So the ultimate objective of the network is to minimize this error and improve the network's performance on the given task. And what you see on screen is actually a simple network with 3 types of layers. The input layer is the one which receives the initial data or features that are fed into the network. Each neuron in the input layer represents a feature of the input data. Now, the hidden layers are the ones between the input and the output layers. There can be 1 or more hidden layers. These layers perform complex calculations, computations on the input data. Each neuron in the hidden layer is connected to every neuron in the previous and the subsequent layers. And the output layer is the one which provides the final result or prediction based on the processed information from the hidden layers. The number of neurons in the output layer depends on the nature of the problem. For example, if it's a binary classification problem, you have 1 neuron with a value of 1 or 0. And if it's a multi-class classification, you could have as many neurons as the number of classes, and so on. So the inputs or the x1, x2, x3 can be either scalar. In this particular example, it is a scalar, but it can also be vectors in case of text embeddings, or tensors in case of, which is an array of numbers in case of images. So all neural networks have a training process, right? And also an inference process. The training process is the process of training a machine learning model on a labeled data set. During training, the model learns to make predictions by adjusting its internal parameters, such as the weights, based on the input data and the corresponding target values. The prediction pipeline is the process of using a trained model to make predictions on new unseen data points. In the example above, you can see that the input is an image, is a set of images. So you're training your model with a bunch of images as the training samples, and the output is actually the label. So note that typically you would have at the output what is called a softmax layer, which actually makes sure that the values are between 0 and 1. So you have a distributed probability of each class. So in this particular case, the inference, you can see that you show an image of a cat, and the output label is actually the distributed probability of all the classes. In this particular case, it's not shown how many classes. The diagram doesn't show that. But typically, if you take ImageNet and those type of neural networks out there, they have got thousands of classes. So you have a huge vector of 1,000 elements, and then you will find the particular class having the highest value or highest probability is actually the output label. Now, every neural network is trained with a data set containing inputs and outputs such that while the input data traverses through the different layers of the network, the error in its prediction of the output from the expected value is held to a minimum. So that way, the way you do that is by adjusting your weights through the gradient descent. So what you see here are actually 2 plots of the loss function of 2 neural networks, with and without any kind of optimizations like regularization, skip connections. These are, think of the optimization like you're trying to get to the bottom of a hill basically where the loss is the minimum from a position where the loss is high. The quicker you can reach the bottom will determine how well the performance of the network is, how good the performance of the network is. So sometimes you may have to do things like, maybe choose smoother activation function, or maybe tune some hyperparameters. By the way, hyperparameters are the configurations that you do before the training, like the number of hidden layers, whether you want the learning rate, like the step at which you get down from your hilltop to the bottom, what kind of steps that you use for that. So these are all like hyperparameters. So you can adjust hyperparameters. You can use smoother activation functions. You can do skip connections, and there are lots of techniques that you do to smoothen this kind of descent, gradient descent, so that your performance, because during training, you're actually feeding a lot of samples. Initially, the weights are random, so you get an output value which is different from the expected, and then you calculate the error, you back propagate, you adjust all the weights of all the layers, and then you try again with another sample, and so on. So you keep trying, you keep throwing all your training data, and you keep back propagating at times different. There's something called batch size. So after the batch size, that's when the back propagation happens, and then you adjust the weights, and then again you try, and then you repeat this. They call it epoch. So you retrain with all your training data for a number of epochs, and that's how you make the model perfect, so that you can start doing inference. Okay, natural language. One of the most popular applications of generative AI is ChatGPT, as you all know. It was actually built on years worth of researches in natural language processing. And one of the basic concepts of natural language processing is to represent every word as a vector or embedding. So word embeddings are these dense vector representations of words in a continuous vector space, where words with similar meanings or contexts are represented by vectors that are close to each other. So as you can see here, this is actually taken representing word to vec, which we'll just take a look at, where sentences from books or articles, they're like fed into a neural network, and as part of the learning process, we'll see how it learns. But then, as part of the learning process, you are actually generating these values for these words, or embeddings for these words. These are all vectors, and basically, as part of the training process, you are actually understanding the semantic relationships, the syntactic relationship, the linguistic relationship of all these words. So that actually paved the way for all the future developments. So word2vec. So how are these word embeddings generated? So word2vec was one of the early neural networks that did that. It learns word vectors by predicting the context words of a target word in a large corpus of text. So CBAW is called continuous bag of words. So you can see here that it predicts a target word given the context. So in this example, you can say that there are 5 words, hope can set you free. And out of these 5 words, you can have a window of the first 3 words. You pass in the one hot vector encoding. So one hot encoding means for each position of the word, your vocabulary is actually 5 in this example. So hope can set you free, it's 5. So there is a position for each word. So you put a 1 wherever you have that particular word. So for hope, it is 10000. For set, it is 00100, and the word can is 01000. So that's the output. So imagine you are taking each sentence and you have this window, and you are actually feeding the neural network, which actually has a single hidden layer here. You have input layer, you have the hidden layer, and the output layer. And the dimension of the hidden layer is just 3. So it's a toy example here. So So the value of the hidden layer is actually used as the embedding for the output word. So in this particular toy example, it's just a three-dimensional embedding. Whereas in Word2Vec, actually, there's a hyperparameter, which is a parameter that you pass in to ask it to set the hidden dimension. So instead of 3, you can set it to 100, 200, and so on. In reality, the actual size embedding of a word embedding, like BERT is a very popular model, natural language processing model. There, the size of embedding is fixed, and it is 768. So the more the number of the more the size of the embedding, the better knowledge that it can it can store. And for GPT-3, by the way, it is 2048. That is the and we don't know about GPT-4. I mean, they don't release these kind of information, but then GPT-3 is well known. It's 2048. Now here you can see the words being represented as a 7-dimensional vector, and then you are able to visualize it in 2D space. So there is something called dimensionality reduction. And there are programs that you can write to do the dimensionality reduction so that you can visualize how a word embedding looks like, so that you can see in space how it is So there is Google has got a tool called projector.tensorflow.org, which I'm just clicking now. Hope you can see that. So this is actually a Word2Vec with 10,000 words or something. And they have actually done a dimensionality reduction, and they're plotting the words in 2D space. Now, if I click that, you see all the related words here. See here, when I said Braves, it picked up all these. And if I select, let's just keep clicking a few of these. So when I said not, the nearest point is, it said MPH, kilometers, ships, battleships, speeds, and so on. And if I select, let me select Cleveland, it said Cincinnati, Browns, Ohio, Baltimore, Sox, Philadelphia, Chicago. So these are the words that form a cluster somewhere near Cleveland. And if I said metallic, you see all the words: alloys, metals, crystalline, and so that is kind of the way Word2Vec works. But Word2Vec is one of the earlier is one of the I hope you can still see my screen.
We sure can.
Okay. So Word2Vec is actually one of the early models. So after that came BERT, and BERT had a lot more information. Word2Vec, as you see, the way it was trained was, it just set the context. Like you have a window, you have input words, and you just have the target word. But that is really not the way, because if you have the same word having a different meaning in the same sentence, how do you represent those? So there are some problems with Word2Vec. Okay, Smart Compose, I know many of you have used in Gmail. It's a feature that uses a deep learning model, specifically a type of recurrent neural network, or RNN, to suggest completions for sentences as users type their emails. Essentially, RNNs can be considered as a series of interconnected neural networks, each processing one input at a time step and having a hidden layer that maintains the information across the time steps. And another way of visualization of the RNN is if you were to unfold or unroll a single cell across multiple time steps. You would essentially get a series of interconnected cells, each processing one input at a time step, with the hidden state being propagated from one time step to the next. So Smart Compose utilizes an RNN to predict the next word or phrase in a sentence based on the preceding context. As a user types an email, the RNN considers the entire sentence up to that point to generate suggestions for what the next word or phrase could be. The problem with the RNN though, is that it doesn't have memory, and so it tends to forget words at the beginning of the sentence when you reach the end. So there are networks like long short long short-term memory, or LSTM, that resolves this issue. But there is one research that happened in 2017 that would change the world of artificial intelligence forever, and that is transformer. So the transformer architecture actually spelled the death knell to several previous architectures in AI. It was introduced in the paper in 2017 by Vaswani and et al. It's called Attention is All You Need. So the transformer model revolutionized NLP by introducing this concept of self-attention mechanism. So it allows it to process input data in parallel, like all the words are in parallel, not like RNN. But then it also captured the complex relationships between different words in a sentence. So basically, it kind of took one word, each word in the sentence, and said, how much influence does the other words have on this word? And that was called attention. And it calculated what is called the attention score. So the higher the attention score, the more the influence is. And while in the process of calculating the attention score, there are weights, and it is those weights that are being learned by the model. So the transformer contains two components. The encoder. Before that, let me just focus on this particular picture, where the bolder lines means that there's a very strong attention. So you can see here, pointing to a word on this, the cells word on the right side. You can see the it being, it is referring to the cells. So the attention shading appears to confirm that it and boring refer to the cells. So as you feed sentence after sentence after sentence to the model, it is this attention between these words that is being recorded or captured as knowledge, and the weights, the adjustment of the weights as it gets trained, is what builds that knowledge in the model. The transformer contains two components, the encoder and the decoder, both of which uses the attention mechanism. But there are models that uses the encoder part alone, like the BERT. So the BERT uses just the encoder part, and we'll come to how it works by just using the encoder part. And there are models that just use the decoder part. GPT, from which ChatGPT was derived, is actually that. Basically, you feed in the input, it generates output. And whereas with BERT is a model designed for tasks like sentence classification, question answering, named entity recognition, and more. It uses only the encoder component of the transformer. It is pre-trained on a massive corpus of text using what is called the masked language model. It learns to predict the max. So basically, you feed in sentences, and it masks randomly words, and it tries to predict the embedding of the masked word. And of course, the weights are initialized with random values initially, but then through back propagation, the weights get adjusted till it's able to predict the right kind of word for the masked word. So it happens in an unsupervised manner. So you just feed it text, and it just masks, and it kind of trains the weights automatically. So that's called the masked language model. Now, GPT is a model designed for generative tasks like text generation, text completion, and more. It uses the decoder component of the transformer. So the decoder is essential for tasks where generating sequence is important, as it allows GPT to generate coherent and contextually relevant text. Now, during training, GPT uses a sliding window method, much like the word2vec we mentioned a while ago. where a window of 2048 tokens, so that is the input size of GPT-3, that is considered as the input, and the next single word is assumed as the output. So the sliding window is then shifted by a fixed number of tokens or words to generate the next sample. So that's how the samples gets generated for training. And you know how big GPT is. I mean, it is called a large language model because it's been trained with millions of articles, books, and whatnot. And GPT-4 is there are images as well, and so on. So the mass language model, I think I covered mass language model. Okay, so let's go to the next. So this is the translation AI. So the diagram here shows the architecture of a transformer-based language translator. The input sentence is converted to a numerical representation and encoded into a deep representation by a 6-layer encoder. The encoder and the decoder consists of self-attention and feed-forward layers, and the decoder also contains an encoder-decoder attention layer with an input of the deep representation created by the last layer of the encoder. So if you look at the visualization of the encoder self-attention between the first two layers, you can see how the strong attention link between the magazine and the gun. It suggests why it ultimately did the translation as Zasobnik in Czech, which means gun magazine, rather than Kasopis. Kasopis in Czech means news magazine. So instead of gun magazine, instead of news magazine, it did find the relationship with the gun magazine. The attention link between woman and her illustrates how the system internally learns co-reference, meaning the same thing. That her and the woman both are same. So that is again some knowledge that the model has learned. And you can see the two colored heads. They call it heads. You can have a single head, you can have multiple heads. So in this particular case, one head is learning a different aspect about lexical meaning of the two words, the orange colored, and the other one is learning the gender representation in the language, in the particular language. All right, so we are into GPT and the LLMs. GPT-3 was the most popular model from OpenAI until recently when GPT-4 came out with multimodality. Even GPT-3 evolved into its present shape through several iterations. First, you have the base LLM, then the instruct GPT, which is an instruction-based LLM, where they introduced reinforcement learning with human feedback, or RLHF. And later, a safety layer was added in the November 2022 release of ChatGPT, which was designed for conversational interactions. So that's why the safety was important. So with the advent of GPT, also came an explosion of large language models, or LLMs. LLMs became popular because they are capable of performing various tasks such as text completion, translation, summarization, question answering, and more with fine-tuning or prompt engineering. So it's like with LLMs, with large language models, you didn't have to fine-tune or retrain your models like before, like in the case of BERT. In the case of BERT, the pre-trained model came with a lot of understanding, but then if you want to use that model for your use case, let's say a sentiment analysis or a named entity recognition, or summarization, whatever, question answering, you needed to train the model using your data, and then you had to attach an output layer that would actually give you the output. So that was because it had only the encoder. Whereas with GPT, especially after extremely large models were built with so much of data, it could be you could use those models with prompting as opposed to as opposed to fine tuning or retraining. And this tree actually shows the evolution of large language models, particularly the explosion of GPT models in 2023, like the GPT-4, Claude, Bard, Llama, Anthropic, and so on. So you can see how the focus is now on decoder-only models or GPTs, and there's so much of open source models that are being built. So this actually shows the RLHF in action. Like I mentioned earlier, GPT-3 undergoes initial pre-training on a large corpus of text from the internet, books, articles, web scraped content, Wikipedia, and so on, using the decoder part of the transformer model. This step helps the model learn the grammar, the semantics, the syntax, the facts, reasoning abilities, and some level of understanding of different topics. However, there is an additional step to fine-tune these foundation models called RLHF. So that is what makes GPT or ChatGPT and other GPT-4 so powerful. Because for RLHF, actually a prompt is used to guide the model towards generating the desired outputs. And human experts provide demonstrations of correct and desirable outputs for a set of prompts. So these demonstrations serve as a reference of what the model is expected to generate. And using human demonstrations as a reference, a comparison data set is created where multiple alternative completions for each prompt are ranked according to human judgment. So there are people sitting and ranking these results. Of course, a sample set of data set. This data set is used to train a rewards model. So there's another model here, another neural network. It's a rewards model, which is a component that assigns a numerical score or reward to different completions of a given prompt. An algorithm termed proximal policy optimization adjusts the main LLM's parameters to maximize the expected rewards. So you want the main LLM to maximize the expected rewards according to the rewards model. So the rewards model guides the proximal policy optimization algorithm by providing the rewards that are used to compute the gradients for updating the model's parameters. So essentially, the rewards model serves as a guiding signal during fine-tuning. So in this particular case, you can see the prompt was the prompt was a dog is a furry animal or a man's best friend. So which is best suited for the context? So these questions are once a model is tuned using RLHF, it's probably it predicts a dog is man's best friend or something like that. So depending on the context. So that is what gives GPT this powerful reply, which is almost accurate most of the time. Okay, GPT 3.5 was trained on a massive data set. So how was it trained? What kind of data set was used? So you can see here it shows you what part of was it used for training. And you can see in GPT-3 was trained with I think the first one was Bard and the next is GPT-3. Bard was trained with a lot of multi-language text. So that's why I tried an experiment by write a poem on using Malayalam, and it did a decent job. Bard did a decent job, but GPT was hallucinating, way too much. So that's because it's not been used for training. Okay, code generation AI models, and this is something that as programmers, as developers, everybody have started using this code generation AI models of late, and I think that's going to replace the process of writing code because writing natural language and having the code generated is pretty much going to be the way people build applications in the future. So they're typically trained on large corpus of code from various sources, including open source projects, code repositories, and other programming sources. Models like OpenAI's Codex, the open source Star Coder, Code Llama based on Llama 2, with code generation capabilities, and similar models are examples of code generation AI models. And I have tried a few of them. There is one called phind.com, where you just instruct it in natural language and it generates a code. It's pretty accurate. I found that it's pretty accurate. And I heard the CEO of that company saying that their goal is to make it perfect, which means the code should work right away. And I think once that happens, then everybody would use natural language. Okay, image generation. So I think I'll skip the GAN because we might be running out of time. So GAN is the adversarial network is one way, but then that was succeeded by models like stable diffusion. It's an interesting technology, where it's able to generate images from a text prompt. So actually it generates the image from a 4 by 64 by 64 image of pure noise and conditioned by text. So that's what you see in this slide, a dog wearing a hat, and you see how from a simple noise image of 4 by 64 by 64, and the one shows the data set, which is one, so that it's just one image, and then that goes in, and it's actually an embedding. It uses an embedding of the noise, and then it's fed into a neural network called UNet, and it is actually a noise predictor. So the thing is, you divide the generation process into 50 steps. I mean, that is configurable, and you kind of incrementally you have your complete noise. During the first step, you reduce a little bit of noise, then you reduce a little bit of noise, and so on until you get the image. And of course, this model has been trained. I mean, what you're seeing now is the actual generation part, but during training, the reverse process, which means the images have been fed in, so which we'll see now. So this is actually the process of how the final image is generated from the noise in steps. So initially you start with full noise, and then you reduce the noise, and finally you have the image. And it has been conditioned by text. So what is diffusion in stable diffusion? So the principle of diffusion is based on simulating a series of transformations on a noise signal, so to gradually generate a realistic image. So the process starts with an initial noise signal, which serves the starting point for generating the image. It involves iteratively updating the noise signal through a series of steps, and at each step, the noise signal is modified to gradually transform it into a more structured and realistic representation. So during the training process, so that's important, during the training process, the generative model learns the transformations that are applied at each step of the diffusion process. So the model's objective is to generate noise signal that, when passed through these transformations, produce images that are indistinguishable from the real images. And here you see how the training occurs. You pick a training example from the training data set. So you need a training data set. Like every neural network, you need a data set. And that data set is, for each picture, you have got 50 slices, 50 samples, and each with a little bit of noise added, until the last one where you have so much of noise. And the objective is, so in this particular slide, you see the step 3, and at step 3 there is the image and there is some noise, and then the model's job is to predict the noise. So it is a noise predictor, And what it does do, just like other neural networks, it compares the actual noise, because you know the actual noise, because you are as part of the training data set, you are creating all these samples. So you know, little bit by little bit, you are adding the noise. So you know the actual noise, you know what the unit is predicting or the model is predicting. Okay, so I was actually going through the Stable Diffusion training process, where you see, with you pick a training example from the training data set, and for that particular step, it's able to predict the model predicts the noise, and that is basically the model. That's basically the training process. And here you could see that the noise predictor has been conditioned with the text provided in the form of text embedding. So you merge the text embedding with the vision embedding, and then the output of the final layer before the classification is in a reciprocal network can be considered as a vector embedding of the input image. So that's why the vision embedding and the text embedding is together being used to condition the particular model. So this embedding represents a very high level feature representation of the image, capturing relevant information. So you can see that the attention layer, just like we talked about text attention a while ago on text embeddings. We talked about self attention, which is like what is the influence that each word has on the next word. In this particular case, what is the influence that the word has on the part of the image? Which part of the image is influenced? So that is why when it says a dog wearing a hat, that hat is actually influencing that area of the image. So that is why it's able to understand that it's called cross attention. In the case of text, it is self attention. In the case of video, it's cross attention. All right, so now we come to the LLM applications and frameworks. And two of the frameworks that is most popular in this area is LangChain and Llama Index. LangChain is an open source framework that helps developers create applications using large language models. It provides a standard interface for what are called chains, where you could build a sequence of LLM queries and responses and have many integrations with other tools and so on. And Llama Index is another open source framework for LLM-based applications to ingest, structure, and access private or domain-specific data. Now, recently I noticed that with that OpenAI Dev Conference, it's looked as though they are doing everything as part of their latest GPT-4 release, and also the APIs. It's doing pretty much everything that LangChain and Llama Index does, like agents and RAG, retrieval, augmented generation, and so on and so forth. So we'll touch upon that. Okay, coming to the prompting mechanism. That slide shows actually three techniques of model learning. You can learn through pre-training. That's how BERT, original pre-trained model, works. You can fine tune it with your data, and then there's the prompt-based tuning. So we mentioned masked language model in BERT, so that's a pre-training part. You can fine tune it. You can perform, with your data. However, in prompt-based fine tuning, as seen in GPT models, we just need to design your template where you specify. So you can see in the prompt-based, the last in the case C, prompt-based fine tuning, you can see that you're giving a demonstration for the two labels, like positive, a fun ride, it was great. And for a demonstration for the negative label, the drama discloses nothing, it was terrible. And now, if you, as part of the prompt, you say, no reason to watch, it was dash. And if you let the model do the completion, it would say it was terrible, right? Because that is basically the way prompting works. So you give it a few examples, and then you pose your question, it'll give you the completion. So the components of a prompt, this is the actual data, input data that the LLM is expected to process. That is the sentence being either classified or being summarized, the document being summarized, and so on. So that's the input data. And then you have examples. You need to provide a few concrete examples of the how the input output pairs look like. Then you can give instructions like you can textually describe what to do. So that is an instruction. And then you can give indicators like providing input to an LLM in a fixed and predictable structure. So you can put hash instruction. So these are all tips that you can use while creating your prompts. And then, of course, the context. So beyond the components described above, if you want to provide some extra context like your own data, that's your context. So these are the things that you provide in your prompt. And retrieval augmented generation is a natural language processing technique that uses artificial intelligence to improve the quality of responses. And RAG retrieves data from external sources of knowledge to make large language models more accurate. So if you have your own enterprise data and you don't want to retrain or fine-tune the model, you can actually use RAG or retrieval augmented generation, where you first chunk the documents, the documents that you have, and index them into what are called vector databases to build the knowledge base. And then when you query something, the query is converted to a vector embedding, because now with natural language processing, one of the first things that you do is you have a sentence, you can generate a vector embedding, and you can look up the matching chunks to your query, and then you retrieve those and use those and put it into the prompts. Just like I mentioned in the earlier slide, one of the things that you can put in the prompt is actually the context. And the way you retrieve the context is what I described here. And once you have retrieved the relevant chunks from the knowledge base in the vector database, we can modify the prompt and then feed it into the LLM to get the relevant response. Now, this it was a core feature of Llama Index and LangChain, but apparently with OpenAI, the latest OpenAI APIs, it does everything by itself. Okay, that brings us to the last section, which is the agents. The agent is the additional layer or system built around the LLM. Now, the agent provides higher level control, context management, behavior coordination for the conversation. It can handle tasks such as interpreting user instructions. So it's basically, as the diagram shows, it is built around an LLM, which does the reasoning part. But then you can say that, by the way, I've got these tools to do things. Like, for example, I have this tool to create a schedule, or I have this tool to book a ticket. I have this tool to send a instant message to Slack, and so on. So, and you tell the LLM that these are the tools that I have available. And while you chat with the LLM, you can actually, the LLM actually detects indications of using the tool, and then the LLM will actually can invoke the tool to do the action. And then so you can just imagine the kind of opportunities that this gives you. And in fact, one of the demos that I saw at the OpenAI Dev Day was just this. Basically, it was a chat GPT type of thing where you say, I want to look at my schedule, and then it gave control to a tool that actually brought down your schedule, and then you said, okay, I have it looks like and it also said there's a conflict. I mean, that was something that the LLM reported. And then you said, okay, I need to send this message to my boss saying that I have a conflict, so I won't be able to attend it. And it immediately used a different tool to send an instant message to the individual. So this is, as you know, prompts are the input to the LLMs that make it think and reason. And chain of thought prompting is a technique that provides the LLM with a sequence of intermediate steps that lead to the desired answer. And likewise, React is actually a technique that combines reasoning and acting. And in fact, React is what enables agents, the tools, because in as part of the React process, it reasons and then acts. So it prompts language models to generate both verbal reasoning traces and actions. It enables dynamic reasoning, high-level planning, and acting. And there are a lot of agent open source implementations that I have tried, and most of them have works, and some of them get stuck, gets into an infinite loop. So auto agent is one. So this is one example that I tried where I wanted to plan an event. So it created all these agents automatically, and it created an event planner, it created a web designer, it created an email communicator, and it generated the code for sending emails. It generated the code for doing a web design, and so on and so forth. But now, apparently, OpenAI does all that with the latest release of their assistant API. And there is also role playing, so you can have agents assuming roles and then kind of interacting with each other and doing things. So I mean, there are a lot of safety and security issues there. I don't think anybody has addressed all of that. And this is one slide about the OpenAI offerings that they have. They also noticed that on the left hand side, they expose a lot of APIs for usage, and on the right hand side, they also expose APIs for fine tuning the models with your data. So if you want to build an LLM like GPT-4, you can do that. You can train it. Of course, you need to look at all the payment details. And as a footnote, you can see the number of developers, like 2 million developers, 92% from Fortune 500, and 100 million weekly active users. This is what they claim to have. As we go forward, I believe OpenAI is, for example, their assistant API is what is shown here on screen. You see, they've got code interpreter, which is actually the one that generates a code and executes a code. They have retrieval, which is the RAG part, and then they have you can upload files. Basically, it can understand that, and it can do the RAG part, and it can do the prompting and retrieve answers from your and also GPT-4. Apparently, they have reduced the price significantly. 1/3 as it costed before. And apparently, there was one statement that I thought was interesting. It takes $15 to ingest all the Harry Potter books. It takes $180 to ingest all the 8 Harry Potter movies, at 1 frames per second, which is 20 hours worth, and so on and so on and so forth. So the prices have come down a lot. Now, coming back to the challenges, this is the last slide, I think. LLMs are CPU memory hoggers. So you have open source LLMs, you have proprietary LLMs. So right now, with the price reduction of OpenAI, I think a lot of people are going to continue to use OpenAI APIs, and their APIs are now richer. They have agent functionality, they have RAG functionality, and so on. Open source LLMs, again, are expensive to train. There again, OpenAI has got this API to do the training also. The number of input and output tokens is important. Many of the open source LLMs have very limited number of tokens, input tokens, like 4,000. If you want to put the whole document in, you need 100. So GPT-4 Turbo has got 128,000 tokens, so which is huge. And open source LLMs need refinement, like the reinforcement learning with human feedback and so on. And of course, hallucinations and so on. So I think with that, we come to the end. I have this last slide, which is the hype cycle. We are up here, generative AI. I think this is based as of 2023. It still will take a few hours, few years before it becomes, before it is usable across the board. So I think we all will be waiting for that, I guess. I think I'll take a couple of questions. I think already we are delayed. So I think I'll take a few questions. If somebody can, post it on the chat, that'll be great. Okay, I have this question. Will generative AI be used for writing code in the near future? Would that get rid of programmer jobs? I would tend to say that the answer is yes. It's already happening. There are, several. Like I said, there are several products already in the market, like the GitHub Copilot, Amazon Code Whisperer, Replit, Find, and so on and so forth. The trend is to write future applications in natural language and let the AI generate the code. Of course, in order for these models to be perfect, they would need to do evaluations. They need to do some post-processing to ensure that there's no safety, security risks, and so on. And I believe already such code LLM companies would be doing that. And I would think it's just a matter of time before it becomes foolproof. And I think programmers in the near future, at least, should start using such tools that would help them implement applications much quicker. And I guess those who don't embrace the new way might just get left behind. That's what I think. Yeah, I can see another question here. Would foundation models remain the monopoly of tech giants? Yeah, I think so, because today it takes a lot of money to build your own large language model. There are, it takes a lot of compute, a lot of money, and there are lots of LLMs available in open source. If you go to Hugging Face, you can see thousands of such models, but they lack the kind of reliability that you find in ChatGPT. Also, OpenAI is now exposing APIs to fine-tune their own models with your data. So if you don't want to do prompting, instead you want to fine-tune with your data, you might as well do that. And considering the economies of scale, which OpenAI benefits from, perhaps it might be cheaper to use their training APIs as opposed to purchasing the necessary compute to build one yourselves and host and deal with all the scaling and so on and so forth. I'll take one last question here. Yeah, here it is. Would there be a market for agents? Yeah, agents, I think, are still in its infancy, and there are a lot of issues related to safety and privacy, because even in that demo, I found that it's all prompt based. So you're actually there's a lot of prompt injection happening, and I don't know whether it's safe, and whether the security is taken care. So OpenAI, they say that you can build GPTs. They call it, they don't call it agents, they call it GPTs. So they also unveiled a marketplace where designers could monetize them. And the demo that they showed, where you can converse with the chatbot and asking it to do various things, was cool. But again, not sure about the safety and the security and privacy aspects. I would like to believe that you would see some nice GPT agents out there, which might eventually have the capability to interface with even other agents, to have some agent to agent conversation and so on. So a lot of possibilities out there, but it remains to be seen. I think with that, we come to the end of this webinar. I want to thank all of you for sparing your time, valuable time to attend this. I'll have the recording shared with all of you. And again, once again, thanks for joining. Have a great day.